Okay, nah sekarang kita now we are going to work with the same file to do the optimization after we have done the data reconciliation for the temperature profile along the reactor in the other video. Right, so basically the same setup for the inlet stream and then the reactor. And then in this case, we do add an objective functions because we want to maximize something. Right, so we create OPT, we can create OPT, and then we put like a linear because we have all the cost functions as in linear and we want to maximize that as opposed to minimize in the DR data reconciliation case. And in the objective optimization case, we define the input as in like the ethylene price minus 40, right? And then the acetic acid inlet flow rate also minus 30, and then the product, the ethylene isn't not really the product, the excess we can sell, assume 40 the same price, but then this is then the main product, which then phenyl acetate, it's a 100, and then this is the AA, the acetic acid as a byproduct like 30, right? So we could only get this number if we run. We can only get this variable if we run the equation oriented in the simulation mode. Say for example, we run this in the equation oriented mode for the simulation mode, yeah, and then we run this. And then here we can see what the variable is. For example, in this case, for the we can see the plant reactor, and then you can look at the value of the flow rate component. This value 10, meaning that is then the flow rate of acetic acid, and in the 10th compartment of the reactor, because we know we have like the length is then 10 meters and then divided by 1 meters, and this is then the flow rate of acetic acid at the 10 meters. So that's basically how you can see all of this from 1 till 10, 1 till 10. Yeah, 0 means it's at the inlet, really inlet, and then 1 meters, 10, 2 meters, until 10 meters, and so on and so forth. So that's basically how you can how we can get this number, and then just put the cost, right? If it's minus, means like minus in the linear objective functions. It's plus, then and it's plus. So we are making money by creating this product, and then we are losing money by consuming this product. That's basically what it is. So once we get it defined in the objective functions, then we need to define what's then the degree of freedom. So we go to the spec groups, and then in the spec groups we create a new spec groups. We have created the recon in the DR case, the characterization case, but now in the case in the optimization case, we are going to create optimization spec group. We go to spec, and then in the optim, in the OPT case group, we are going to vary the oxygen molar flow rate, and then we say it is going to be an optimized parameter, not reconcile, because this is going to be used for optimization. And then the cooling, the temperature of the cooling medium, right? It was 133 degrees C. We're also going to use that as an optimized independent variable, so to say. Okay, and we'll put active, and then we change this from simulation to optimization, and then we don't forget to put the optimization as the objective function, and then we click run. And we can see the control panel, the progress. So 96, 99, 100, 106. Yeah, so it's converged in 166 iteration, So problem converge, and then we can see what the result is in the OPT case. And then we can see the initial value is 0.3. Now we get to the 0.48 or 4.5 as the objective function in dollar per hour. And then for the term results, we can see the the amount of ethylene that is being consumed, right? And then this is then the acetic acid being consumed, and then this is the ethylene going out, what the main product going out, and then so we see 1.4 and then 1.9, and then this is then the acetic acid in the product. So we are having it less. So that's the how we can read the terms in the objective functions, and then we can see the objective function of 0.48. So that's basically how we set up the optimization case using the equation oriented mode in Aspen PLUS.